Okay, a satellite is revolving near by Earth of radius RE. Its velocity is increased root 3 by 2v. Velocity is increased root 3 by 2v, where v is orbital speed of satellite. Then find the maximum distance of satellite from the center of the Earth. Maximum displacement distance of the satellite from the center of the Earth. So that is we are going to discuss. So the satellite is revolving around the Earth. Okay, of radius how much? R. Of radius R. When speed of the satellite increases, then the satellite moves in a elliptical orbit. How much? When the speed of satellite v equal to square root of root 3 by 2 into b. Then what happens here? The satellite is moves in a elliptical orbit. Satellite is moves in a elliptical orbit. Here v is equal to square root of gm by r, orbital velocity. Okay. Then we want to find out the maximum distance of satellite from the center of the Earth. So here the satellite is revolving around Earth. When speed is increases, the path also changes. The path of the satellite also changes. Finally, it revolve in a elliptical orbit. Revolve in a elliptical orbit. This is the center of the Earth. This is the center of the Earth. Okay. And this is the length of the semi-major axis, and this is length of the semi-major axis. When the speed of the satellite is increases to square root of 3 by 2 times of v, the satellite moves in a elliptical orbit. Now, initial kinetic energy of a satellite. Initial kinetic energy is equal to of mv square. Of mv square, that is equal to of m into b is equal to how much here? Square root of 3 by 2b. B means here orbital velocity square root of gm by r. That is equal to gm by r whole square. So of m into 3 by 2 into gm by r, that is equal to how much here? 3g capital M small m by 4r. So initial potential energy of a satellite. Initial potential energy of a satellite. Here initial potential energy. Potential energy is equal to minus g capital M small m divided by r. So we know that total energy of a satellite in elliptical orbit always constant. Total energy total energy is equal to potential energy plus kinetic energy, that is equal to minus G capital M small m by R plus 3 G capital M small m by 4R. So total energy is equal to 4R. So here minus 4 G capital M small m plus 3 G capital M small m. Total energy is equal to what we get here, minus G capital M small m divided by 4R. This is the total energy of a satellite in an elliptical orbit. But total mechanical energy, total energy of a satellite in elliptical orbit is equal to minus G capital M small m divided by 2a. So this is according to our problem, what is the total energy of a satellite? Minus G capital M small m by 4R. So hence minus G capital M small m divided by 4R is equal to minus G capital M small m divided by 2a. So what we get here, A is equal to 2R, length of the semi-major axis. Finally we get here length of semi-major axis, A equal to R. So here when a satellite is revolving in elliptical orbit, when the satellite is reached from this point to this point, the maximum distance of a satellite from center of earth is how much? This total length a plus a 2a minus this radius 2a minus r. So here maximum distance of satellite, from center of earth is equal to 2a minus r, 2 into 2r minus r, 4r minus r, that is equal to how much? 3r. It is equal to 3r. So our answer is 3r. Okay, now let us discuss another problem. When wavelength of light is incident on a metal surface changes from 500 nanometers to 200 nanometers, the maximum possible kinetic energy of emitted photoelectrons becomes 3 times. Then find the work function of a metal. Right. So this problem is based on photoelectric effect. According to Einstein equation, we wrote that H nu is equal to half mv square plus W. H nu is equal to kinetic energy of electric electrons plus work function. Kinetic energy is equal to H nu minus W. So this can be written as Hc by lambda minus W. Hc by lambda minus W. Right. So this is a general equation. Okay. Now kinetic energy is equal to, right, Hc by lambda means how much wavelength used initially, 500 nanometers, that is equal to 5000 angstroms minus W. This is equation 1. Equation 1. This wavelength changes 500 nanometers to 200 nanometers. 5 nanometers to 200 nanometers. Then the kinetic energy of emitted photoelectrons becomes how much? 3 times. Now 3 times of initial kinetic energy is equal to hc pi. So what they given here, 200 nanometers. Initial it changes from 500 nanometers to 200 nanometers. That means here 2000 angstroms minus W, equation 2. Then kinetic energy becomes how much? 3 times of initial kinetic energy. 3 times of initial kinetic energy. Right. Now doing equation 2 divided by equation 1. Divide equation 2 with equation 1. So here 3 by 1 is equal to hc by 2000 minus W divided by hc by 5000 minus W. Okay? Right. What is the value of hc here? hc is equal to 12,400 electron volt. Now 3 by 1 is equal to 3 by 1 is equal to what we write here, 12,400 divided by 2000 minus W divided by 12,400 divided by 5000 minus W. Right. Here 0 0 cancel, 0 0 cancel. Okay, cancel. Now here 3 by 1 is equal to 3 by 1 is equal to 124 divided by 20. So 124, that is nothing but how much here, 6.2 minus W divided by here 124 divided by 50, that is equal to 2.48 minus W. Okay, doing cross multiplication. 3 into 2.48 minus 3W is equal to 6.2 minus W. Right. 3 into 2.48 is equal to how much? 3 into 2.48 is equal to 7.44. 7.44 minus 6.2 is equal to 3W minus W, that is equal to W. So here 2W is equal to 1.24. 1.24. That means W is equal to 1.24 divided by 2. 0.2 electron volts. 0.2 electron volts. So our answer is 0.62 electron volts. 0.62 electron volts. So now let us discuss another problem. An observer line of sight is at P when container of diameter 30 centimeters and height 445 centimeters is empty. So here this is a container, empty container. Whenever the container is empty, an observer sees a point P in the container. What is the diameter of the container here? 30 centimeters. And what is height of the container is 45 centimeters. Right. If this container is filled with the liquid up to 30 centimeters height, he is able to see edge of the container. That means he is able to see at this point edge of the container. Find the refractive index of liquid. Okay, what is the refractive index of liquid? We want to find out. Right. Here this is air medium whose refractive index is 1, and this is a liquid medium whose refractive index is mu. Right. So this is this point P is at 15 centimeters height from the bottom of the container, and this hole becomes 30 centimeters. Okay, right, this is 30, and also this is also 30 centimeters. Now this is 15 centimeters, and this also 15 centimeters. Okay, according to geometry. Now here this is 30, this is 15, and this is 15. This angle must be how much? According to geometry, 45 degrees. 45 degrees. And this is angle of incidence, which this light ray is coming from edge of the container and reaches to observer eye. Okay. Now we apply Snell's law from denser to rarer. Apply Snell's law from denser to rarer medium. That means from water to air. Right. Here N1 sin I1 is equal to N2 sin. Okay. N2 sin R. So N1, this first medium, the refractive index of this water medium is mu into sin I is equal to, what is the second medium here? Air medium. Okay, the refractive index of air medium is 1, that is nothing but sin R. So here R is equal to how much? If this angle becomes 45 and this angle also 45, alternate angles are equal. Right, sin 45. So here mu is equal to sin 45 divided by sin I. Sin 45 divided by sin I. So here sin I is equal to, from figure sin I is equal to opposite side by hypotenuse. That means 15 by square root of 15 square plus this is azimuth how much? 30 square. So here sine I is equal to 15 by, take 15 common, 15 square common, 15 square root of 1 plus, here what we get here, 15, take 15 common, 1 square plus here 2 square. Okay, sine I is equal to 1 by root 5. 1 by root 5. So mu is equal to, here sine 45 is nothing but 1 by root 2. Sine I is equal to 1 by root 5. That is equal to how much here? Root 5 by 2. Root 5 by 2. So our answer is mu is equal to root 5 by 2. Okay, now let us discuss another question. A mass of 2 kg suspended by a string of mass 6 kg. A wave of wavelength 6 cm is produced at the bottom of the string. The wavelength of a wave at the top end of the string will be. That means this is a string. Okay. To this string, a mass 2 kg is suspended. What is the string mass here? 6 kg. 6 kg. So here a wave of wavelength 6 cm is produced at the bottom of the string. This is the bottom of the string. Here the wave is produced. The wavelength of a wave at the top end of the string. This is the P, point P, at the top end of the string. What is the wavelength of a wave? We want to find out. Okay. This is the simple formula, simple problem. We know that V proportional to square root of T, tension. We calculate here tension at point P is equal to mg. That is equal to mg is equal to 2g. Tension at point P, Tp is equal to mg also. That means 6 plus 2, 8g. So here Bb by Vp is equal to square root of Tb by Tp. That is equal to Tb is equal to how much? Tension at bottom point 2g by 8g. That is equal to 1 by 4. That is equal to 1 by 2. But here the frequency remains constant. So we know that V is equal to n lambda. N is constant. N is a constant. So here B proportional to lambda. Vb by Vp is equal to lambda B by lambda P. Okay. Now what is Vb by Vp here? 1 by 2. So 1 by 2 is equal to lambda B by lambda P. We want to find out wavelength of a wave at the top end. That is equal to lambda P is equal to 2 lambda B. That is equal to 2 into 6. That is equal to 12 centimeters. 12 centimeters. So this is the wavelength of a wave produced in a string at the top end is equal to 12 centimeters. 12 centimeters.